The dark side of the moon is not dark at all. For billions of years, it faced away from Earth, hidden and unreachable. No human had ever seen its surface until 1959. The Soviet Luna 3 probe sent back the first grainy images of a landscape utterly different from the side we know. Craters scarred the terrain in numbers that defied counting. The far side held secrets that changed everything we thought we knew about our cosmic neighbor. In 2013, China's Chang'e 3 mission landed on the near side, carrying ground-penetrating radar. The radar pierced 40 meters down through lunar soil and rock. What it found beneath the surface told a story written in layers. The moon's crust runs 3 times thicker on the far side than the near side. This asymmetry is not random. Is something catastrophic shaped our moon into 2 fundamentally different hemispheres. The South Pole-Aitken Basin stretches 2,500 kilometers across the far side. It ranks as the largest impact crater in the entire solar system. The collision that created it happened over 4 billion years ago. That impact exposed material from deep within the moon, material that holds clues to how worlds form and die. NASA's data reveals what textbooks missed. The far side is not just hidden, it is geologically alien compared to the face we see each night. If you find this fascinating, hit that like button and subscribe. We begin now. Look up at the moon tonight. If the sky is clear, you'll see the same face humanity has always seen. The same shadows, the same bright highlands, and the same pattern of dark Maria that some cultures call a rabbit, others a man, others a woman carrying water. Every person who ever lived saw that exact arrangement, because the moon shows us only one side. Always, the moon rotates. That much is true, but its rotation takes exactly 27.3 days. Its orbit around Earth, so, takes exactly 27.3 days. Those numbers match perfectly. The result is a cosmic dance, where one face stays locked toward us while the other remains forever turned away. Picture this. Hold a coin between your thumb and finger. Keep the face of the coin pointed at a candle across the room. Now walk in a circle around that candle, always keeping the coin's face toward the flame. Your hand rotates as you walk. The coin spins, but the flame never sees the back of that coin. Now, the moon does this naturally, locked in position by forces that took millions of years to settle into place. This synchronization has a name: tidal locking. Early in the moon's history, it spun faster. It showed Earth every part of its surface as it rotated, but Earth's gravity pulled unevenly on the moon's near side, creating friction in the lunar interior. That friction acted like a brake. Over millions of years, the moon's rotation slowed. The spin rate dropped and dropped until it matched the orbital period exactly. 2 dancers locked in embrace, turning together, never seeing each other's backs. The moon's face frozen toward us, the other side hidden. I think most people assume we've always known what the whole moon looks like. I certainly did. But the truth is stranger. For all of human history until 1959, no human eye had ever seen 41% of the moon's surface. Every poet who wrote about lunar beauty, every astronomer who mapped the craters, every person who ever looked up and wondered, they were staring at an incomplete world. The hidden hemisphere existed in perfect mystery, closer than Mars, closer than Venus, closer than any wandering planet in the night sky, yet utterly unknown. That far side could have been covered in oceans, and no one would have known. It could have held mountains 10 times taller than anything on the near side. It could have been smooth as glass. For thousands of years of recorded history, humans built telescopes, calculated orbits, landed on continents, sailed every ocean on Earth, and 41% of the moon remained as mysterious as the surface of a distant star. Think about that. And the moon is only 238,000 miles away. That's a distance you could drive in about 5 months if you never stopped for gas or sleep. 5 months on an impossible highway through empty space. Close enough that 12 humans have walked on it. Close enough that we've left footprints and flags and scientific instruments. Yet nearly half of it stayed hidden until the space age began. The tidal lock kept its secret perfectly. There's something else people get wrong about that hidden side. We call it the dark side. The phrase sounds right. Dark equals unknown. Dark equals mysterious. But the far side of the moon receives exactly as much sunlight as the near side. It's not dark at all. When we see a new moon, a thin crescent, or no moon at all, the sun is illuminating the far side. And the hemisphere we can't see is bathed in daylight for 2 weeks straight. Then it rotates into 2 weeks of night. Same pattern as the side we watch. The darkness isn't literal, it's metaphorical. The name is a complete misconception, but it stuck. Actually, we do see slightly more than just one perfect hemisphere. The moon wobbles as it orbits. This wobbling has a name, libration. The moon's orbit isn't a perfect circle, it's an ellipse. That means its orbital speed changes slightly. Sometimes it moves a bit faster than its rotation, sometimes a bit slower. The result is a gentle nodding and shaking motion. Over time, we can peek around the edges. 59% of the moon becomes visible from Earth if you watch long enough and catch it at the right moments. 59%, not 50. And that extra 9% comes from libration, but the remaining 41% stays permanently hidden from direct view. No wobble reveals it. No angle exposes it. From Earth, it simply does not exist. The mechanism that created this lock isn't unique to our moon. Most large moons in the solar system are tidally locked to their planets. Jupiter's moons show the same behavior. Saturn's moons. Even Pluto and its moon Charon are locked to each other, each showing the other only one face for eternity. Tidal locking appears to be the final state of any moon that orbits close enough and long enough. The universe pulls bodies into this configuration, a face that can only look at you, never away. For nearly 60 years now, we've known what's on that far side. Spacecraft have photographed it, astronauts have orbited it, our robots have landed there and sent back data. The mystery is solved in one sense, but knowing what's there and understanding why it's so different are not the same thing. What did we actually find when we finally looked? What makes that hidden hemisphere so unlike the side we've always known? The Soviet probe Luna 3 carried a camera toward the moon in October of 1959. Not just any camera, a system designed to photograph the far side, develop the film automatically in space, then scan each image line by line and transmit it back to Earth. The technology sounds primitive now. It was extraordinary then. On October 7th, 1959, the probe swung around the lunar far side. The camera clicked. Film advanced. Chemical baths developed the images in a miniature darkroom aboard the spacecraft. Then, slowly, the scanner began sending the pictures home, line by line, pixel by pixel, like a fax machine transmitting across 240,000 miles of empty space. The images arrived grainy and blurred. Contrast was poor. Details were smudged. But they showed enough. The far side of the moon, never before seen by human eyes, appeared on screens in Moscow. Scientists leaned in. They stared. Something was wrong. The far side looked nothing like the near side. Where were the dark patches? The Maria, those smooth basalt plains that mark the face we know? The side facing Earth is almost half covered by them. The sea of tranquility, the ocean of storms. Dark patches you can see with your naked eye on any clear night. The far side had almost none of them, just craters, highlands, a rough terrain stretching to every horizon captured in those fuzzy images. The scientists expected symmetry. The assumption was woven into their predictions, their hypotheses, their understanding of how moons form. A sphere should be uniform. Gravity pulls evenly. Material distributes the same way on all sides. There was no reason, no geological mechanism anyone could think of that would make one hemisphere fundamentally different from the other. It seemed impossible. Some thought the cameras had malfunctioned. Maybe the exposure was wrong. Maybe radiation had corrupted the images during transmission. Maybe the film had degraded in the harsh environment of space. The idea that the moon could actually be asymmetric, that it could show two completely different faces, violated basic assumptions about planetary formation, and like opening a familiar book to find the second half written in a completely different language. You expect consistency. You expect the story to continue in the same voice, the same style. Instead, halfway through, everything changes. Different words, different structure, the same book, but somehow not the same at all. More images came down, better images. Soviet probes sent back additional photographs. The asymmetry held. It was real. The moon's far side was a stranger. 9 years later, 3 men saw it with their own eyes. Frank Borman, Jim Lovell, William Anders, Apollo 8, December of 1968. The first humans to leave Earth orbit. The first to see the far side directly, not through transmitted photographs, but through their spacecraft windows as they swung around the moon's hidden hemisphere. The contrast hit them immediately. Borman radioed back descriptions. Lovell took notes. Anders photographed everything he could. They had studied the lunar images. They had prepared for what they would see. Preparation did not diminish the shock. Expecting a mirror, they found a stranger instead. The photographic revelation was like looking at a familiar face in a mirror, then turning around to see its back was scarred beyond recognition. The near side rolls with those dark maria, smooth, relatively flat, younger rock covering older terrain. The far side is bright, rugged, ancient, crater upon crater upon crater, highland terrain dominating almost the entire visible surface. Only a few small dark patches breaking the monotony of pale battered rock. From orbit, the difference is stark. One side tells a story of volcanic resurfacing. The other tells a story of relentless bombardment with no resurfacing to cover the scars. Same moon, same gravity, same age, same formation process, but 2 completely different faces. The astronauts orbited 10 times. Each pass around the far side took them out of radio contact with Earth. They disappeared behind the moon, alone, cut off from every other human in existence. When they emerged, they brought descriptions of a landscape that defied expectation. Not the moon they had imagined, not the symmetrical sphere that theory predicted. The mystery deepened with every photograph, every observation, every detailed map compiled from the Apollo missions that followed. Seeing the far side did not solve the puzzle. It sharpened the question. It made the asymmetry undeniable. Why? But why would one side of the moon be so different from the other? What force, what process, what accident of formation could split a single body into 2 such contrasting hemispheres? The universe doesn't care what we find convenient. It builds worlds according to physics, not our expectations. And physics had somehow built a moon with 2 faces. The answer would require new thinking, new models, a willingness to reconsider how the moon formed in the first place. The answer lies in something called the Great Asymmetry. The moon is not uniform. It never was. When you look at the statistics, the difference becomes impossible to ignore. The maria, those dark lava plains that pattern the near side, cover nearly 1/3 of the hemisphere facing Earth. They're the eyes and mouth of the man in the moon, and they're what gives the near side its character, its recognizable face. The far side? Almost none. Maria on the far side are rare and isolated. Mare Moscoviense, the Sea of Moscow, is one of the few. It sits alone in a landscape dominated by something else entirely. Rugged highlands and craters stacked upon craters, overlapping in layers that record billions of years of impacts. The far side kept everything, every scar, every collision. The near side smoothed over its past. This is not a minor difference. This is a fundamental split in the moon's geology. The moon is a binary world with 2 histories written on its skin. One side, a smooth memoir of lava floods. The other, a violent diary never erased. Picture this. Imagine if Earth's western hemisphere was covered in oceans and the eastern was all mountains and craters. One half of the planet looks like one world, the other half like something completely different. You'd cross the dividing line and step into an alien landscape. That's the moon's split personality. Same sphere, same age, 2 utterly different surfaces. The reason comes down to something hidden beneath the surface. Crust thickness. The near side has thin crust. It averages around 30 kilometers thick. That's about 18.5 miles. 18 miles of rock between the surface and the molten interior below. Not much, in planetary terms. a thin shell over something hot and fluid. The far side? More than double that thickness. The far side crust averages over 60 kilometers. That's nearly 40 miles of solid rock, a thick barrier between the moon's interior and the vacuum of space. This difference explains everything. When the moon was young, it was hot. Magma churned beneath the surface, pressurized and searching for weak points. On the near side, with its thin crust, the magma found those weak points everywhere. Ancient impacts had already cratered the surface, creating basins, depressions, weak zones in the lunar shell. The magma burst through. It flooded those impact craters, filling them like water filling a bowl. The lava spread, cooled, and solidified into the dark plains we see today. The Maria aren't just features, they're flood zones, ancient eruptions that renovated the near side. On the far side, the magma hit a wall. 60 kilometers of crust is a thick lid. The pressure wasn't enough to break through. The magma stayed trapped beneath the surface, cooling slowly in the dark, never reaching the craters above. As those craters remained exactly as the impacts left them. No resurfacing, no smoothing. The far side is a museum that never threw anything away. The near side renovated. This creates the landscape the astronauts saw, the near side they trained on, with its smooth, dark seas. The far side they discovered, with its endless cratered chaos. The thickness difference also means something else, something that wasn't obvious at first. The moon has a heavy side and a light side, not heavy in the sense of mass, but heavy in the sense of crustal material. The far side carries more crust, more rock, more solid structure. This creates an imbalance. The moon is lopsided. That imbalance affects its gravity. It affects how the moon rotates. It affects the way mass is distributed through the entire body. This is not just cosmetic, and the asymmetry proves the moon is not geologically uniform. It formed or evolved with a fundamental imbalance built into its structure. Think about that. The moon didn't just happen to end up with one side facing Earth. The moon has physical reasons for its orientation. The thick side, the heavy side, rotates away from us. The thin side, the lighter side, faces Earth. Gravity and rotation locked that configuration in place over time. But why? Why would the crust form unevenly in the first place? One theory involves Earth itself. When the moon was young and still forming, it orbited much closer to us than it does now, close enough that Earth's influence was immense. Earth is a massive heat source, not just light, but radiation, tidal forces, gravitational stress. All of that energy poured into the side of the moon facing us. And the near side may have stayed hot longer. Earth's radiation kept the minerals from solidifying as quickly. The crust stayed thinner because it stayed molten. The far side, always facing away, cooled faster in the cold of space. Its crust thickened, hardened, became the barrier that trapped the magma below. This is still being studied. Scientists argue about the exact mechanism. Was it heat from Earth? Was it an asymmetry in the moon's formation, baked in from the beginning? Was it both? The truth is, nobody's certain. The data supports the crust thickness difference. The cause is still debated. What's undeniable is the result. 2 hemispheres, 2 geological histories, 1 moon, but functionally 2 worlds stitched together along a dividing line. The Apollo astronauts crossed that line on every orbit. Yes, they flew over the near side, familiar and mapped. They disappeared behind the moon into the far side, alien and hostile. Each crossing was a transition between worlds. Same altitude, same speed, completely different terrain passing below. You can see it in the photographs, side-by-side images of the near and far hemispheres. One looks calm, dark patches breaking up the bright highlands. The other looks like it was hit by everything the solar system could throw at it and kept the receipts. Craters inside craters. No smoothing, no mercy. The great asymmetry forces a reconsideration of how moons form. Conventional models assumed symmetry. A body coalescing from debris would form evenly, cooling uniformly, developing a consistent crust. The moon breaks that assumption. Something about its formation, its relationship with Earth, its early evolution, created an imbalance that persists 4.5 billion years later. This changes how we understand planetary formation. Bodies don't always form symmetrically. Proximity to a parent planet can warp geology. Heat distribution matters. Orbital mechanics matter. The Moon is not an exception. It's a lesson. Other moons in the solar system show asymmetries too. We used to think they were anomalies. The Moon suggests they might be the norm. The universe doesn't build perfect spheres. It builds worlds according to physics, not aesthetics, and physics built a moon with two faces for reasons we're still untangling. The previous section ended with geology, asymmetry, craters upon craters, a moon that breaks the rules. But there's another asymmetry worth considering, a one that has nothing to do with rock or impact basins. This one is about what it feels like to go there. Every spacecraft that orbits the Moon spends time on the far side, nearly 50 minutes per orbit, and during that time, all contact with Earth is severed, not degraded, not weakened, cut. The Moon itself blocks every signal. Radio waves travel in straight lines. They don't bend around obstacles. When the bulk of the Moon sits between you and home, you're alone in a way that's hard to describe. Michael Collins understood this better than most. Collins was the command module pilot for Apollo 11. While Neil Armstrong and Buzz Aldrin walked on the lunar surface, Collins orbited above, alone, for 21 hours. That's nearly a full day. He circled the Moon 30 times while his crewmates explored Tranquility Base below, and for half of each orbit, he passed behind the Moon into complete radio silence. No voices from Houston, no telemetry updates, no confirmation that anyone even knew he was still alive. Collins later reflected on this isolation with a striking bit of arithmetic. At that moment in history, there were roughly 3 billion people on Earth, plus 2 on the surface of the Moon, and then there was him, separated from all of humanity, all 3 billion plus 2, by the sheer bulk of the Moon. Not just distance, a physical barrier so massive that no voice, no signal, no electromagnetic whisper could reach him. Collins was the loneliest man in history, not because he was far from people, because he was separated by a wall of stone so thick the universe itself went silent. Picture being in a room where the door doesn't just close. The entire building ceases to exist on the other side. You can't call out. You can't check if anyone's there. The building is gone. That's what radio blackout feels like. You know Earth is still turning. You know people are still going about their lives. But from where you sit, there's no evidence, no proof, just the instrument panel and the window and the grey landscape rolling past below. Radio silence isn't just quiet. It's the universe holding its breath. The astronauts who flew these missions described the far side in vivid terms. Some called it a battlefield frozen in time. Others said it looked like an endless junkyard, craters stacked against craters with no pattern, no relief, no dark Maria to break up the monotony. Just impact after impact, had preserved in airless stillness. The view was harsh, unforgiving, and during those 48 to 50 minutes behind the Moon, it was the only view there was. But the psychological shift wasn't just about loneliness. It was something deeper, something the astronauts didn't fully anticipate. Researchers later termed it the absence effect. On the near side, astronauts could look out the window and see Earth, a blue marble hanging in the black, a reminder of home. Every person they'd ever known, every place they'd ever been, all of it visible, right there, framed in the window. Distant, yes. Small, yes, but present. On the far side, Earth vanished completely. Not distant, not small, gone. Erased from view as if it had never existed. And many astronauts reported this as more profound than seeing Earth from space in the first place. Seeing Earth from orbit is awe-inspiring. Everyone knows that image, the pale blue dot, the fragile sphere against the void. But that experience still includes Earth in the frame. You can see it. You can orient yourself by it. The far side offers no such comfort. Turn your head, scan the windows, search the sky. Nothing. Just stars and the relentless grey of ancient craters. The absence effect isn't about being far from home. It's about home disappearing entirely from your reality. Even if you know it's there, even if you trust the orbital mechanics that will swing you back around to the near side in another 20 minutes, the visceral experience is one of complete separation. Some astronauts described it as peaceful. Others found it unsettling. Most reported both feelings at different moments during the same mission. And think about that for a second. You're traveling faster than any human in history. You're seeing sights no one else has seen. You're part of an achievement that will be remembered for centuries. And yet, for nearly an hour at a time, you're more alone than anyone has ever been. Alone in a way that isn't just physical distance. Alone in a way that involves the removal of every connection to the species you belong to. Collins kept working during those silent passes. He ran checklists. He photographed landmarks. He monitored systems. The work continued because the work had to continue, but he also had time to think, time to sit with the silence, time to look out at the far side and realize just how strange his situation was. He later said he didn't feel lonely in the tragic sense. He felt aware of the distance, and aware of the stone wall between him and everyone else. Aware that if something went wrong during those 48 minutes, no one could help him. No one could even hear him call. That awareness changes a person. Not always in dramatic ways. Not always in ways that show up in post-flight interviews. But it leaves a mark. Every astronaut who has orbited the moon has spent time in that silence. Every one of them has watched Earth disappear behind 3,000 kilometers of rock and dust. Every one of them has felt the weight of being the only conscious mind in that particular slice of space. The far side doesn't just look different, it feels different. The lack of contact, the absence of Earth, the endless battered terrain rolling past below. It's a place defined as much by what's missing as by what's there. And that absence, that silence, that profound separation from everything familiar is part of what makes the far side so uniquely significant. Not just as a geological curiosity, as a reminder of what isolation actually means when you strip away every buffer, every connection, every comforting voice from home. The silence isn't the only strange thing about the moon. There's something else, something we didn't discover until we could actually touch the surface and leave instruments behind. The moon moves, not through space, that's orbital mechanics. It moves internally, it shakes, it vibrates. It responds to forces we can barely detect from Earth. We used to say the moon was dead, geologically inert. Actually, that's not quite right. It's just dying very, very slowly. There's a difference. Starting with Apollo 12, our astronauts placed seismometers on the lunar surface. Not just one mission. Apollo 14 left instruments. So did 15 and 16. These weren't quick experiments. They operated continuously until 1977, nearly a decade of listening to the moon's interior, nearly a decade of waiting for it to move. And it did move. The first major discovery came almost immediately, when spent rocket stages were deliberately crashed into the surface to create controlled impacts. The seismometers recorded something unexpected. The moon rang, like a bell, not for seconds, not for minutes, for over an hour. A single impact would set the entire body vibrating, and those vibrations would continue, barely diminishing, for longer than most movies run. Picture hitting a wine glass with a spoon, at that clear tone that hangs in the air for a moment before fading. The moon does that, except the tone doesn't fade. It keeps going, and going. The entire sphere of rock resonating like struck metal. The reason is simple, once you think about it. Earth has water, atmosphere, soil with moisture, forests and oceans and layers of sediment that absorb vibrations. Sound travels through our world, but it dissipates quickly. All that fluid, all that complexity, acts like a damper. The energy spreads out and vanishes into heat. The moon has none of that. No water to absorb the shock, no atmosphere to carry energy away. Just rigid, dry stone. Ancient rock that hasn't felt rain or wind or flowing liquid for billions of years. When you strike it, there's nothing to stop the vibrations. They just echo endlessly, yet through solid material that might as well be one enormous tuning fork. Imagine hitting a glass with a spoon and the tone lasting through an entire movie, through the opening credits, through the climax, through the closing scene, still ringing as the final frame fades to black. That's what happens when you drop something heavy on the moon. The whole world becomes an instrument. This wasn't just a curiosity. The way vibrations traveled through the lunar interior told scientists what was inside. Different materials transmit seismic waves at different speeds. Dense rock behaves differently than loose rubble. Solid material behaves differently than molten material. By tracking how long it took vibrations to travel from impact site to seismometer, and how those vibrations changed along the way, researchers could map the moon's internal structure without ever drilling a hole. The data revealed something surprising. Deep inside, roughly 350 kilometers down, there's a core. Not a large one, not compared to Earth's molten interior, but it's there, partially molten, still liquid after 4.5 billion years. The moon isn't a solid ball of rock all the way through. It has a heart, small, cooling, but not yet frozen. That core is roughly 350 kilometers in radius. To put that in perspective, that's about the distance from New York to Detroit, a sphere of partially molten material. Deep beneath all that dead cratered surface, still warm, still moving, a remnant of the violence that created the moon in the first place. The seismometers picked up something else. Moonquakes. Actual seismic events. Not many, not strong, but regular, measurable, real. Some of these moonquakes came from deep inside. They occurred at specific times in the lunar month, always at the same depth, always following a pattern. The cause became clear quickly. Earth's gravity. The same tidal forces that pull our oceans into bulges also pull at the moon's interior. As the moon orbits, different parts of its structure feel varying gravitational stress. Deep inside, where the rock is still slightly warm, slightly plastic, that stress builds and releases over and over. A rhythm dictated by orbital mechanics. Those deep quakes were expected. Once researchers thought about it, tidal forces made sense. The shallow moonquakes were different. These occurred much closer to the surface. They weren't tied to Earth's tidal pull. They didn't follow the orbital rhythm. They were irregular, unpredictable, and they suggested something most people don't associate with the moon: ongoing geological activity. Right now, not billions of years ago, today, the moon is shrinking. Not quickly, not dramatically, but as its interior cools, the entire body contracts. The volume decreases. The crust, already solid, has nowhere to go. It crumples, folds inward, like a grape drying into a raisin. The skin wrinkling as the flesh shrinks beneath it. The moon's surface is doing the same thing, slowly, over millions of years, but measurably. Those shallow moonquakes are the sound of the crust adjusting. Fault lines slipping, rock fracturing under stress, the moon settling into a slightly smaller configuration as the heat leaks away into space. It's not dead, it's dying. There's a difference. Death is static. Dying is a process, an ongoing transformation. Think about that for a second. The moon you see in the sky, the same moon that's hung above Earth for billions of years, is still changing, still creaking, still settling. The surface you see in photographs, frozen and ancient, is actually shifting, imperceptibly, but shifting. The seismometers stopped operating in 1977. Budget cuts ended the program, but they'd recorded enough, thousands of seismic events, years of data, a complete portrait of a world that turned out to be far more dynamic than anyone expected. We thought we'd find a dead rock. Instead, we found a cooling ember, still warm at the center, still responding to Earth's pull, still contracting as the last remnants of its formation heat radiate away into the void. Yet the moon isn't a fossil, it's a slow-motion collapse, a 4.5 billion year death that won't finish for billions more. And all of that, the ringing, the moonquakes, the molten core, the shrinking crust, remained hidden until we actually went there, until we placed instruments on the surface and listened. The moon doesn't broadcast its secrets. You have to get close. You have to touch it. You have to wait in the silence and pay attention to the vibrations traveling through stone that remembers the beginning of everything. But what about the places you can't touch? What about the side of the moon that never faces Earth, hidden until we sent spacecraft to look? What about the interior, locked beneath kilometers of rock? The answer is you learn to see without looking. In the 1960s, NASA sent 5 robotic probes to orbit the moon, the Lunar Orbiter missions. Their job was simple: map the surface, find landing sites for Apollo, photograph the terrain in enough detail that astronauts wouldn't come down on top of a boulder or into a crater. They did that. They mapped beautifully, but they also did something else, something nobody expected. They got pulled off course. The spacecraft would be gliding along, tracking perfectly, following the predicted path. Then suddenly, without warning, they'd veer. Not much, just a tiny deviation, a slight acceleration here, a slight deceleration there. Something was tugging at them, something invisible, something heavy beneath the surface was pulling the spacecraft toward it, then releasing it as they passed overhead. The spacecraft became plumb lines, while pulled by invisible anchors of dense rock below. Engineers thought it was a malfunction at first, thruster issues, measurement errors, but the deviations kept happening, always in the same places, always over the same craters. The Lunar Maria, those dark patches visible from Earth, something beneath those plains was denser than the surrounding rock, much denser. They called them mascons, mass concentrations, buried pockets of material so heavy they warped the moon's gravity field. We discovered the moon's internal structure not by drilling or landing, but by watching spacecraft get tugged off course. The mascons were so strong they would destabilize orbits and crash satellites if not accounted for. The moon's gravity is lumpy, full of ghosts from ancient impacts. Think about that. We mapped the invisible by watching the visible get pulled. Mapping the moon's gravity is like running your hand over a sculpture in the dark. You can't see it, but you can feel the heavy parts pulling at you. Your spacecraft is your hand. Gravity is your sense of touch. And the moon becomes knowable not through light, but through force. This became the blueprint for everything that followed: remote sensing, indirect measurement, reading the moon, not by what it shows you, but by how it behaves. It's reading a book by weighing it. You learn from what you can't see directly. In 1994, a Department of Defense satellite called Clementine spent 2 months in lunar orbit. It carried cameras, yes, but also sensors that could detect different wavelengths of light: infrared, ultraviolet, frequencies that reveal composition, and not just shape. Clementine looked at the permanently shadowed craters near the poles and found something odd, a signal that hinted at hydrogen, possibly water ice, possibly. The data was fuzzy. The orbit wasn't ideal, but it was enough to make scientists wonder. 4 years later, Lunar Prospector arrived, a small spacecraft, barely bigger than a washing machine. It carried a neutron spectrometer, a device that measures neutrons bouncing off the surface. When cosmic rays hit the moon, they kick neutrons out of the soil. Those neutrons scatter. Some escape into space. Some get absorbed by hydrogen atoms if hydrogen is present. By counting the neutrons that escape, you can infer what's hiding in the dirt. Lunar Prospector orbited for 1.5 years. It mapped the entire moon, and it strengthened the evidence. Hydrogen was there, but concentrated in the coldest craters, the places where sunlight never reaches. We still hadn't landed. We still hadn't scooped up a sample, but we were seeing through stone, through shadow, through the limitations of being far away. The real breakthrough came in 2009. The Lunar Reconnaissance Orbiter, LRO, still operating today, still mapping. It carries 7 instruments, cameras that can resolve features smaller than a meter across. You can see the Apollo landing sites, the lunar rovers, the tracks left by astronauts in 1972, shadows frozen in dust for 50 years. But LRO did more than photograph. It measured temperature. It mapped radiation. It counted neutrons like Lunar Prospector, but with better precision. It built a topographic map of the entire moon, far side included, accurate to within meters. Every crater, every ridge, every shadow. The far side, which humans didn't even see until 1959, is now mapped in higher definition than most of Earth was a century ago. Then came GRAIL, the Gravity Recovery and Interior Laboratory. Two identical spacecraft, launched in 2011. They didn't carry cameras. They didn't carry spectrometers. They carried one instrument, a radio. Their job was to fly in formation, one following the other, separated by about 200 kilometers. That's roughly the distance from New York to Philadelphia. As they orbited, the moon's lumpy gravity would pull the lead spacecraft slightly faster or slightly slower, depending on what was below. The distance between the two spacecraft would change by a few micrometers, by less than the width of a human hair. As they measured that change, constantly, precisely, for months, the result was a gravity map so detailed you could see ancient impact basins buried under billions of years of lava. You could see where the crust was thick, where it was thin, where massive chunks of dense material had punched through and settled deep below the surface. GRAIL mapped gravity anomalies precisely, not just the big mascons, but the subtle variations, the fingerprints of impacts that happened before Earth had continents, before Earth had oceans. The moon's interior became visible, not through drilling, not through seismic waves, though those helped, but through gravity, through watching two small robots fall toward each other and measuring how fast they fell. You don't need to touch something to know it. You just need to watch how it pulls. How the far side is no longer dark to us, not in the way it once was. We've photographed every square meter. We've measured its composition from orbit. We've mapped its gravity. We know where the crust is thin, where the mantle is close to the surface, where ancient magma seas left pockets of dense rock that still tug at anything passing overhead. We can see what we can't photograph. We can know what we can't touch. The tools changed, the methods evolved, but the principle stayed the same. If you want to understand the moon, you have to listen. You have to pay attention to the small deviations, the tiny tugs, the ways it reaches out and pulls at the things we send. The moon doesn't hide its secrets on purpose. It just doesn't make them easy. You have to ask the right questions. You have to measure the right things. And sometimes, the answer comes not from what you see, but from how hard the moon pulls you toward it. The question now is why. Why is the moon lopsided in the first place? The answer takes us back 4.5 billion years, back to when the Earth was barely formed, back to an event so violent it shaped everything that followed. The leading explanation is called the giant impact hypothesis. The idea is this: a Mars-sized object, something we now call Theia, slammed into the early Earth. The collision vaporized rock. It sent massive plumes of debris spiraling into orbit. That debris cooled. It clumped together. It formed the moon. The impact was like ringing a bell so hard it shattered. Then watching the pieces fall back together into something new. The energy released was unimaginable. Enough to melt the surface of both bodies. Enough to turn solid rock into an expanding cloud of molten droplets. The Earth survived. Theia did not. What remained of it either merged with Earth or scattered into space. What ended up in orbit became our moon. This is not a fringe idea. It is the most widely accepted theory for how the moon formed. The evidence is strong. The moon's composition matches Earth's mantle. Its lack of iron matches what you would expect if it formed from outer layers, not a core. The isotopes in lunar rocks are nearly identical to Earth rocks. That similarity only makes sense if the moon came from Earth, or from something that collided with Earth and mixed its materials together. But the giant impact does not explain the asymmetry, not directly. Theia's collision created the moon, yes, but why is one side so different from the other? One possibility is that the collision itself determined which side faced Earth. The moon formed close, very close, within 15,000 miles of Earth, maybe closer. That is close enough that Earth's gravity locked one face toward us almost immediately. And that matters, because the near side, facing Earth, absorbed heat. Radiation from the young Earth kept it hot longer. The far side cooled faster. When magma rises through crust, it prefers the path of least resistance. The near side, staying warm and thin, became the easier route. Lava flooded the basins there. The far side, cooling quickly, thickened. Its crust became a barrier. Magma could not break through as easily. That is one explanation. It is elegant. It fits some of the data. But there is another theory, a stranger one. The moon may have eaten its twin, a second, smaller moon that collided and merged, leaving the far side as a burial mound of crumpled crust. The idea goes like this. When Theia impacted Earth, the debris cloud that formed the moon might have been unstable. Instead of condensing into one body, it split. Two moons formed, one large, one much smaller, maybe a 30th the size. They orbited Earth together for millions of years, but their orbits were not stable. Gravity nudged them closer. Eventually, they collided. The collision was slow, not a violent smash, but a gradual merging. The smaller moon pancaked onto the larger one. Its material spread across the surface. It did not melt, it just crumpled. A layer upon layer of crust piling up on one hemisphere. That hemisphere became the far side, thick, rough, battered not by external impacts, but by its own sibling. The evidence for this is circumstantial. The far side's crust is thicker, yes. Its highlands are more prominent, but we have not found definitive proof that a second moon existed. We have not found a smoking gun. There is a third possibility. The South Pole-Aitken Basin, the massive impact crater on the far side, one of the largest in the solar system. That impact was catastrophic. It punched through the crust. It exposed the mantle. It sent shockwaves rippling through the entire moon. Those shockwaves could have redistributed material. They could have thickened the crust on the opposite side. They could have created the asymmetry we see today. Or maybe all three explanations are partially correct. Maybe Earth's heat shaped the near side. Maybe a second moon merged and thickened the far side. Maybe the South Pole-Aitken impact rearranged everything afterward. The moon's history is not a single event. It is a cascade. One thing happening after another, each one altering what came before. We don't really know why the moon is lopsided. That is the honest answer. We have theories, good ones, but the moon is not talking. Not yet. The data we have now is incomplete. The samples from the near side tell one story. The rocks brought back by Apollo missions. The soil analyzed by Soviet landers. They all come from the Maria, the dark basaltic plains that cover less than a third of the moon's surface. We have almost nothing from the far side. No samples. No soil, no rocks we can hold and measure and date. The far side remains mostly a mystery, not because we cannot see it. We have photographs, we have orbital data, we have gravity maps. But photographs do not tell you when a rock formed. Gravity maps do not tell you what a mountain is made of. You need to touch it. You need to bring a piece home. China's Chang'e missions are changing that. Chang'e 4 landed on the far side. It sent a rover to explore the surface. Chang'e 5 returned samples from the near side. Chang'e 6 is planned to do the same from the far side. When those samples arrive, we will know more. We will date the rocks. We will measure their composition. We will compare them to what we already have. Maybe the answer is in the rocks. Maybe it is not. The asymmetry is one of the moon's defining features, and it shapes how we see it, how we study it, how we think about our own planet's history. Because the moon is not separate from Earth, it is a piece of our past, a fragment of the collision that could have destroyed us, but instead gave us a companion. Theia's collision did not just create the moon. It may have created the asymmetry by determining which side faced Earth and absorbed radiation. Or it may have created two moons that later merged. Or it may have set the stage for later impacts to carve the asymmetry into existence. The answer is still out there, waiting in the rocks, waiting in the data, waiting for us to ask the right questions and measure the right things. The moon does not give up its secrets easily. It makes you work for them. It makes you earn each answer, and even then, yes, the answer often comes with more questions attached. The moon keeps its secrets in layers. Some are written on the surface in craters and mountains. Others are hidden below the crust in structures we cannot see. The asymmetry is one secret. The mascons are another. They are invisible. They are powerful. And they have been pulling at spacecraft since we first tried to orbit the moon. A mascon is a mass concentration, dense material buried beneath the lunar surface, creating a gravitational anchor that tugs at anything passing overhead. The name sounds technical. The effect is simple. Imagine a stone sitting on a trampoline, creating a dimple in the fabric. That dimple pulls other objects toward it. A mascon does the same thing with gravity. We discovered them by accident. In the 1960s, a lunar orbiter spacecraft started veering off course. The trajectories did not match the predictions. Engineers checked the calculations. They checked the instruments. Everything looked correct, but the spacecraft kept drifting. Something was pulling them. Something no one had anticipated. The moon's gravity was not smooth. It was lumpy, uneven, full of invisible anchors that pulled spacecraft downward as they flew overhead. These were the mascons, ghosts of gravity left by violence 4 billion years ago, still reaching up from the surface to affect anything that came too close. They form in the aftermath of giant impacts. A massive asteroid slams into the moon, hollowing out a basin kilometers deep. The crust fractures. Mantle material rises. Later, volcanic eruptions fill the basin with dense lava, layer after layer. And that lava is heavier than the surrounding crust, much heavier. It settles into the basin like lead poured into a bowl. The basin becomes a gravitational trap. Flying over a mascon is like driving over a pothole you cannot see. The spacecraft drops slightly, pulled downward by the extra mass below. If you are not expecting it, if you have not accounted for it in your trajectory, that drop compounds. Orbit after orbit, the spacecraft drifts lower. Eventually, it spirals into the surface. The early lunar orbiters did not last long. Without precise maps of the mascons, maintaining a stable orbit was nearly impossible. Some spacecraft had to be carefully managed just to survive a few months. Others were deliberately crashed before the mascons could pull them down uncontrolled. The moon's gravity was not just uneven, it was full of traps. And think about that. The impacts that created these basins happened billions of years ago. The asteroids are gone. The lava has cooled and hardened. The surface has been battered by countless smaller impacts since then. But the mascons remain, dense anchors in the crust, invisible from the surface, still affecting everything that orbits above them. The moon does not forget its wounds. It carries them as gravitational scars. Grail mapped them with extraordinary precision. 2 spacecraft flying in formation, measuring the distance between them down to fractions of a micron. As they passed over a mascon, the lead spacecraft felt the pull first and accelerated slightly. The distance between them changed. That change revealed the mascon's location and strength. Grail found them everywhere, beneath Mare Imbrium, beneath Mare Serenitatis, and beneath the great basins on the far side that we cannot see from Earth. The mascons are stronger on the near side, much stronger. The maria there are filled with thicker layers of lava. More mass means more gravitational pull. The far side has mascons too, but they are weaker. The basins there are not as deeply filled. Some are barely filled at all. The asymmetry shows up even in gravity. One more way, the 2 sides of the moon refuse to match. Mascons are so strong, they can crash satellites if you ignore them. Even now, maintaining a stable lunar orbit requires constant adjustment. You cannot just put a spacecraft in orbit and leave it there. You have to account for the mascons. You have to plan your trajectory around them or compensate for their pull. The moon's gravity is not a smooth sphere, and it is a landscape of invisible mountains and valleys, each one tugging at your spacecraft in different directions. This matters for future missions. Every orbiter, every communications satellite, every navigation system we place around the moon, they all have to deal with the mascons. The longer you stay in orbit, the more the mascons matter. A mission lasting weeks might get away with rough corrections. A mission lasting years needs precise maps and constant monitoring. The moon does not make it easy. The mascons also tell us about impact history. Where they are reveals where the giant basins formed. How strong they are reveals how much lava filled those basins afterward. The pattern of mascons is a record of the moon's most violent era, written in gravity instead of rock. We can read that record now. We can measure it. We can use it to understand when the impacts happened and what came after. There is something haunting about mascons. They are remnants of catastrophe, frozen in the moon's structure. The impacts that made them reshaped the surface. The lava that filled them poured from the interior over millions of years. All of that is finished now. The basins are cold. The lava has solidified, but the gravitational signature remains, an invisible echo of events so ancient that Earth was still a molten ball when they happened. You cannot see a mascon. You cannot photograph it. You can only feel its pull, a spacecraft drifting lower than expected, a trajectory bending slightly downward, the numbers not matching the predictions. That is how you know it is there, an anchor in the crust, pulling at everything above it, a ghost of gravity that refuses to let go. The moon is not a simple sphere with uniform density. It is a patchwork of different materials and structures, each with its own gravitational signature. The mascons are the strongest features in that patchwork. They dominate the gravity field. They shape what orbits are stable and what orbits decay. They are invisible anchors holding on to the past, still affecting the present, still waiting to pull down any spacecraft that does not respect them. The mascons tell us the moon is complicated. Gravity is uneven. The structure is layered and scarred. That is not the only invisible signature written into the far side. There is another one even more profound for what we might learn from it. Silence. Not the silence of an empty room, not the kind you experience when the noise stops, as the silence of a place that has never heard the roar of human civilization. The far side of the moon is the quietest place in the inner solar system, not for human ears, for radio astronomy, and that changes everything. Earth is loud, not in a way you can hear, but if you could see radio waves the way you see light, Earth would be blinding. Every satellite overhead broadcasts signals. Every radio station transmits. Every cell phone tower pulses with data. Even your microwave oven leaks radiation when it heats your food. All of it adds up. All of it drowns out the faint whispers coming from deep space. Trying to do radio astronomy from Earth is like trying to hear a whisper at a rock concert. The signal you want is there, somewhere, but it is buried under a wall of noise so thick you have no chance of separating it out. And some frequencies are completely hopeless. You could build the most sensitive antenna ever designed, point it at the darkest part of the sky, and still hear nothing but the roar of human technology bouncing off the atmosphere. The moon is different, the far side, specifically. It has something Earth will never have. A shield 3,500 kilometers wide, made of solid rock, blocking every single radio transmission from our planet. 3,500 kilometers. That is the moon's diameter. The entire bulk of it sits between the far side and Earth. No signal gets through, not satellite broadcasts, not radio stations, not the hum of billions of devices all transmitting at once. The moon does not have an atmosphere to bounce signals around. It does not have a magnetosphere to trap charged particles, and it is just cold stone, older than most of Earth's crust, sitting there like a fortress wall. And on the other side of that wall, there is quiet. The far side is a cathedral of silence dedicated to listening, not speaking, a place where the cosmos can finally be heard without the roar of human civilization. That silence is not an accident of geography. It is an opportunity, one we cannot replicate anywhere else in the inner solar system. Mars has no moon big enough to hide behind. Venus has no moon at all. Mercury is too close to the sun, which screams in radio frequencies. The asteroids are too small and too exposed. There is nowhere else to go. The far side is the only listening post. What could we hear from there? Frequencies we have never accessed. Wavelengths that tell the story of the universe before the first stars ignited, and before galaxies formed, before anything in the cosmos produced light. Astronomers call it the Dark Ages. That is not a metaphor. It is a technical term. After the Big Bang, the universe cooled. Electrons and protons combined into neutral hydrogen. The cosmos went dark. No stars yet, no galaxies, just hydrogen gas filling space, cooling slowly, waiting for gravity to pull it together. That period lasted 400 million years, longer than the entire history of complex life on Earth, and we have never seen it. We cannot. The light from that time is gone, redshifted into radio wavelengths, long wavelengths, the kind that get blocked by Earth's atmosphere and drowned out by human transmissions before they ever reach a telescope. But they would reach the far side, place a wire antenna there, stretched across the regolith, and you could detect them. You could listen to the universe as it was 13 billion years ago, before the first star formed, before the cosmic dawn. A far-side radio telescope would be a stethoscope pressed to the chest of the cosmos, listening to its first heartbeat 13 billion years ago. The signals are faint, unimaginably faint, a whisper from the edge of time, stretched and weakened by the expansion of space itself. Detecting them requires more than just sensitive equipment. It requires a place where there is nothing else to hear, no interference, no noise, no contamination from modern technology. The far side is that place, the only place. Scientists have proposed designs, arrays of simple antennas spread across craters, each one just a wire on the ground. No dishes, no moving parts, just metal conductors picking up the faintest radio hum from the early universe. The antennas would be low frequency, tuned to wavelengths longer than the length of a football field. Frequencies so low they are useless on Earth, but on the far side, they would open a window into a time we have never observed. This is not a distant dream. The technology exists. The designs are ready. What is missing is the infrastructure, a way to get the equipment there, a way to power it, a way to relay the data back to Earth, since the far side has no direct line of sight to our planet. Those are engineering problems, hard ones, but solvable. The science is waiting. The questions are lined up. What did the universe look like during the Dark Ages? How did the first structures form? When did neutral hydrogen start clumping together under gravity? How long did it take before the first stars ignited and flooded the cosmos with light again? We do not know. We have theories, models, simulations, but no observations, no data. The far side could give us that. Think about what that means. Every telescope we have ever built looks at light. Visible light, infrared, ultraviolet, X-rays. All of it is light from objects that already exist. Stars, galaxies, black holes. We are studying the universe after it grew up, after it became complicated. The far side would let us study it as an infant, before anything interesting happened, before stars, before galaxies, just hydrogen and time. That hydrogen is still out there, filling the space between galaxies. Most of it is neutral, cold, invisible to optical telescopes, but it emits a faint radio signal at a specific wavelength, at 21 centimeters. That signal has been stretched by the expansion of the universe. The farther back in time you look, the longer the wavelength becomes. Signals from the Dark Ages have been stretched to wavelengths several meters long. You cannot study those from Earth. The atmosphere blocks them. Human radio noise drowns them out. You need the far side. The moon is not just a rock, not just a satellite, not just a place astronauts visited once and left footprints. It is a tool, a natural observatory built by the same collision that gave Earth its oceans and its tilt. The far side is not wasted space. It is a resource, one we have barely begun to think about using. Other telescopes will join the radio arrays eventually. Optical telescopes on the far side would not deal with atmospheric distortion. No clouds, no weather, and no light pollution, just a stable platform with 1/6 Earth's gravity and a view of the stars that never wavers. Infrared telescopes could study the coldest objects in the universe without interference from Earth's warm atmosphere. The far side is not just quiet in radio frequencies. It is quiet in every sense. Geologically dead, atmosphereless, undisturbed by wind or rain or life. A blank slate, waiting for instruments. The Cathedral of Silence is empty right now, waiting. The signals from the Dark Ages are washing over it every second, passing through the regolith, unheard, unrecorded, lost. They have been doing that for billions of years. They will keep doing it until someone puts an antenna there to listen. The universe does not care whether we hear it or not, but we should care, because those signals carry a story. The story of how everything began, how matter organized itself, how the darkness ended, how the first light broke through. That story is written in wavelengths we cannot access from Earth. The far side is the only place we can read it. The far side holds something else, not just quiet radio skies and stable ground for telescopes. something hidden in the geometry itself. Think about the poles. Think about craters there, deep ones, ancient ones. Their rims stand high above the lunar surface, but their floors lie far below. The moon's axis barely tilts, just 1.54 degrees. Earth tilts 23.5 degrees, which gives us seasons. The moon barely leans at all. The sun never climbs high in the lunar polar sky. It skims along the horizon, forever low. This creates something extraordinary. Her craters near the poles have floors that never see sunlight. Not rarely, not occasionally, never. For billions of years, the sun has circled the rim, but never reached the bottom. These are the permanently shadowed regions. The cold traps, Shackleton Crater, Faustini, Haworth, Cabeus, names from another age given to vaults that predate complex life on Earth. Stand at the rim of one of these craters and you could be in daylight. Meters away, at the bottom, there is darkness that has lasted 4 billion years. The temperatures down there drop below -230 degrees Celsius. That is colder than Pluto, colder than most places in the outer solar system. Your helmet lamp would cut only a narrow cone into the black. Depths colder than Pluto, darker than any cave, holding ice older than complex life on Earth. Yet this is the part that gets me. These craters have been collecting water from comet impacts for eons. A comet strikes somewhere on the moon, vaporizes on impact. Water molecules drift across the surface as gas. Most of them escape to space or get broken apart by solar radiation. But some of them, just by chance, drift into one of these permanently shadowed craters. They settle onto the floor. The temperature there is so low that they freeze instantly, and then they stay. They never melt. They never evaporate. The sun never reaches them. They just wait. Patience measured in billions of years. The cold traps are chemical archives where the universe has been filing away samples for 4 billion years, waiting for us to read them. We suspected this for decades. Hints from radar, spectroscopic signatures that suggested maybe, possibly, there could be ice, but we needed to know for certain. 2009, NASA launched the Lunar Crater Observation and Sensing Satellite, LCROSS. The mission profile was simple and violent. Send a rocket stage to the moon, crash it into one of these permanently shadowed craters, see what comes out. They chose Cabeus Crater, a vault that has never been opened, until we smashed the door with a rocket traveling 9,000 kilometers per hour. That is faster than a bullet, faster than anything most of us will ever experience. And the Centaur upper stage weighed 2,200 kilograms. All that mass, all that speed, straight into the ancient floor. The impact vaporized rock, threw up a plume of debris 35 kilometers high. The L-Cross spacecraft followed 4 minutes behind, flying through the plume, instruments recording everything, before it too smashed into the surface. The data came back. Scientists analyzed the spectral signatures. What they found was not a trace, not a hint. The plume contained hundreds of kilograms of water vapor and ice, plus methane, ammonia, carbon dioxide, organic compounds. The frozen library had opened. Let that sink in. The moon is not dry. It holds hundreds of billions of tons of water ice in these shadows, not trace amounts. Enough to drink, enough to grow food, enough to split into hydrogen and oxygen for rocket fuel. The barren moon, the dead world we thought we knew, is actually a resource depot. We just needed to look in the darkest places. This changes everything about how we think of the moon. Every mission before Apollo 17 treated it as a destination, a place to visit and leave. The ice changes the equation. The moon can sustain us. The far side, with its unique geography, has deeper craters, more permanent shadows. The South Pole-Aitken Basin, the largest impact structure on the near side that extends onto the far side, contains some of the deepest cold traps. That asymmetry we talked about earlier, the thicker crust, the ancient impacts, they created the very features that now hold the resource we need most. There is something else at the poles, and the opposite of permanent shadow, high ridges and crater rims that catch sunlight almost constantly, the peaks of eternal light, places where the sun never sets, just circles the horizon endlessly. Solar panels there would generate power continuously. No lunar night to survive. No batteries needed for 2 weeks of darkness. Picture this. You could stand on a peak in near constant sunlight. Look down a few hundred meters into a crater that has not seen light since before the Cambrian explosion. Warmth and cold, light and dark, resources and energy, meters apart. These features exist because of the far side's history, the giant impacts that thickened the crust, the lack of mare flooding that preserved the ancient topography, the moon's minimal axial tilt. All of it conspired to create places where volatiles could hide for eons and where sunlight could shine forever. Geology and orbital mechanics and deep time. Building a library we are only now learning to read. The shadows are still there, still cold, still dark. The ice is still accumulating, molecule by molecule. Whenever a comet fragment strikes and sends vapor drifting, the archives are still being written. We have only read the first page. Cabeus was one crater. There are dozens more, each one a different composition, different ages of deposits, different stories about where the water came from and when it arrived. The moon holds answers in its coldest places, not just about resources, about the history of water in the inner solar system, about where Earth's oceans came from, about whether the building blocks of life were delivered by impacts or formed here. The ice remembers. We just have to ask. The archives of ice are incredible treasures, but there's something else on the far side, something older, something that makes every crater we've talked about look like a dimple. Picture a wound that never healed, a scar so vast it dominates an entire hemisphere, a crater that swallows continents. The South Pole-Aitken Basin. It stretches nearly 2,500 kilometers from rim to rim. That's the distance from Los Angeles to New York, from London to Baghdad. South Pole-Aitken would swallow the United States whole, from coast to coast, with room to spare, and it plunges deeper than the Grand Canyon, more than 8 kilometers down, a wound that never healed. Yeah, this isn't just the largest impact structure on the moon, it's the largest impact structure in the entire solar system, bigger than anything on Mars, bigger than anything on Mercury, bigger than the massive craters on Jupiter's moons. Nothing else comes close. The moon wears the biggest scar in the neighborhood, and we only discovered it recently because it's on the far side, hidden, waiting. The basin stretches across the southern reaches of the far side. If you stood at the rim and looked toward the opposite edge, you wouldn't see it. The curve of the moon itself would hide the full enormity. The horizon would cut off before you reached the other side. That's how big it is. Too large to see all at once, even standing on its edge. Something hit the moon here, early, and in the first 500 million years of the solar system, when planets were still forming and debris still littered the inner worlds. The impactor was enormous, dozens of kilometers across, maybe hundreds. We don't know exactly, but it was moving fast, tens of kilometers per second. The impact that created this basin was like dropping a mountain from space at highway speeds multiplied by 100. The energy released was unimaginable. Vaporized rock, molten ejecta thrown across the lunar surface, shock waves rippling through the entire moon. The impact may have contributed to the crustal asymmetry we talked about earlier. All that molten material, all that energy, redistributing mass, thickening the crust on the far side even more. The basin itself became a geological textbook ripped open. As because this impact didn't just crack the surface, it went deeper, much deeper. 8 kilometers down into the lunar crust. The crust on the far side averages around 50 kilometers thick, in some places, even more. But here, in the South Pole-Aitken Basin, the impact excavated so much material that it may have punched through entirely, exposing the mantle, the layer beneath the crust that we almost never see. Think about what that means. The mantle is different, different composition, different minerals, different story. On Earth, we get tiny glimpses of mantle material when volcanoes dredge it up, when tectonic forces push it to the surface. But the moon doesn't have plate tectonics, no active volcanoes, no conveyor belt bringing deep material up. The mantle stays hidden, locked away beneath the crust, except here, in this basin, where a titanic impact did in seconds what geology couldn't do in billions of years. Scientists have been studying the basin for decades, trying to understand what's down there, trying to confirm whether mantle material really is exposed. The data is complicated. Spectroscopy from orbit shows unusual compositions, minerals that match what we'd expect from the mantle: olivine, pyroxene, materials richer in iron and magnesium than typical crustal rock. But confirming it requires more than remote sensing. It requires going there, collecting samples, bringing them back to labs on Earth where we can analyze them atom by atom. China's Chang'e 4 mission landed in the South Pole-Aitken Basin in 2019. The rover analyzed rocks, sent data back, found materials consistent with deeper origins. But one rover, in one spot, can't tell the whole story. The basin is enormous, 2,500 kilometers across. You could land 100 missions and still only scratch the surface. This is geology on a scale we're not used to. We study Earth by drilling, digging down, extracting cores from the crust. The deepest hole we've ever drilled is about 12 kilometers, and that took decades. The moon is offering us a shortcut, a window into the interior, already excavated, already waiting. The age of the basin is still debated. We think it formed somewhere between 4.3 and 3.9 billion years ago, before the late heavy bombardment, before most of the lunar surface features we recognize today. It's one of the oldest features still visible, ancient even by lunar standards. And because it's so old, it's been modified, battered by billions of years of smaller impacts, filled in places with debris. The original bowl shape has been softened, eroded, not by wind or water, but by impacts. Tiny meteorites, larger asteroids, each one chipping away at the rim, each one adding a layer of complexity. The floor of the basin is not smooth, it's cratered, pockmarked with younger impacts, some of them large enough to be basins themselves, craters inside a crater, layers of history stacked on top of each other. Reading the basin is like reading a book where every page has been written over, multiple times, in different languages, but the story is still there, buried in the composition of the rocks, in the distribution of minerals, in the magnetic anomalies that suggest ancient, solidified pools of molten material. The South Pole-Aitken Basin holds answers about the moon's formation, about its interior structure, about the violence of the early solar system. It's also a reminder of scale. We think of the moon as small. Compared to Earth, it is. But this basin alone is larger than many countries, deeper than the deepest parts of our oceans. The moon is a world, not just a rock, a world with its own history, its own scars, its own secrets. The basin sits on the far side, mostly hidden from Earth. We never saw it until we sent probes around the moon, never knew it existed. One of the largest geological features in the solar system, and it was invisible to us for all of human history, just sitting there, waiting in the dark. We're only beginning to understand what it means, what it can teach us. The samples we collect from South Pole-Aitken won't just tell us about the moon, and they'll tell us about planetary formation, about how crusts and mantles separate, about the violence that shaped the early solar system and built the worlds we see today. The basin is a library, and we've only just opened the cover. The moon is a library of invisible fields, ghosts of a magnetic shield that died billions of years ago, leaving only whispers in the rock. We can't see them, but they're there, written into the surface, carved into stone. A hidden history of something the moon once had and lost. The moon has no global magnetic field today, no protective bubble like Earth's. The solar wind hits it directly, unfiltered, unshielded. This has been true for billions of years. But it wasn't always this way. Some of the Apollo rocks are strongly magnetized. Not all of them, but some. The magnetization is locked into the minerals, frozen in place, like a recording that can't be erased. These rocks are proof. The moon once had a magnetic field, a real one, strong enough to leave permanent marks in the stone. The magnetized rocks are like fossils of the moon's youth, when it had a beating heart of molten metal, something churning deep inside, generating currents, creating a shield. For hundreds of millions of years, the moon was protected. Then the core cooled, the currents stopped, the field collapsed. Gone. Here's the thing. Small worlds aren't supposed to have magnetic fields. They cool too fast. Their cores freeze solid. The moon is small, smaller than some planets' moons. It should have cooled quickly, locked up tight, but it had a dynamo anyway, for hundreds of millions of years. And this challenges our assumptions about planetary dynamos. It suggests the moon's interior was more active, more complex, than a simple, impact-formed body should be. The moon wasn't supposed to do this, but it did. The evidence is still there, not just in the rocks. On the surface itself, lunar swirls, bright, sinuous markings scattered across the moon. They look like calligraphy painted on stone, ribbons of brightness against the darker regolith. Some of the most striking are on the far side. Others, like Rhina Gamma, are visible from Earth with a good telescope. They're beautiful, admittedly, but they're also deeply strange, like finding graffiti that paints itself. The swirls aren't painted on. They're not deposits. They're not caused by composition. They're maps. Maps of magnetism. Places where localized magnetic fields still exist, trapped in the crust. Remnants of the ancient dynamo. These fields are weak, tiny compared to Earth's, but they're strong enough to deflect the solar wind. Just barely. Just enough. The solar wind carries charged particles, protons, electrons, radiation. When these particles hit lunar soil, they cause weathering, chemical changes. The surface darkens over time. This happens everywhere on the moon, constantly. But where the localized magnetic fields exist, the solar wind can't touch. The particles are deflected, turned away. The soil stays bright, unweathered, fresh. The swirls are actually maps of magnetism, places where the solar wind can't touch. They're fossils of the ancient field, visible records of invisible protection. The moon is telling us its own history and writing it across its face in brightness and shadow. Scientists have mapped these magnetic anomalies. There are dozens of them, maybe hundreds. They're not randomly distributed. Some cluster near impact craters. Some align with each other. Some are isolated. The patterns are still being studied. The origins are still debated. But the conclusion is clear. The moon once had a global magnetic field. Then it lost that field. But pieces remained, trapped in the crust, locked in stone, still deflecting the solar wind billions of years later. Think about what that means. The moon had a molten core, convection currents, a dynamo, for long enough to magnetize huge volumes of rock, long enough to create a shield. This requires heat, lots of it, sustained over geological time. Where did that heat come from? The moon formed from a collision. The debris disk coalesced. The interior should have cooled relatively quickly. Tens of millions of years, maybe. Not hundreds of millions. Unless something else was happening. Tidal heating, perhaps. The moon was closer to Earth when it was young. The tidal forces were immense, flexing the interior, grinding rock against rock, generating heat. Or maybe the core took longer to solidify than we thought. Maybe the moon's interior was enriched with radioactive elements, heating from the inside, keeping the core liquid. We don't really know. That's the honest answer. The magnetized rocks tell us the moon had a dynamo. They don't tell us why. The swirls are a reminder. The moon was once protected, shielded, like Earth is now. Then the protection failed. The shield collapsed. The solar wind came rushing in. The surface began to weather, a darkening over billions of years. Except where the ghost fields remain. Those places stay bright, unchanged, frozen in time. The moon is a library of invisible fields, but the library is incomplete. The records are scattered. Some pages are missing. Some are contradictory. The Apollo missions brought back magnetized rocks from a handful of sites. We have localized measurements, orbital data, but we don't have the full story. We don't know when the dynamo started. We don't know exactly when it ended. We don't know if it was constant or intermittent, pulsing on and off, flickering. The far side has its own magnetic anomalies, some of the strongest, in fact. They weren't discovered until we sent probes around the moon, whole swirl systems, vast fields of brightness, invisible from Earth, waiting in the dark. Each one is a piece of the puzzle, a clue to the moon's hidden youth, a marker of something that no longer exists. There's something humbling about this. The moon had a magnetic shield, a beating heart, an active interior for hundreds of millions of years. Then it stopped. The heart went silent. The shield fell. The moon became the dead world we see today, bombarded, unprotected, slowly darkening under the endless solar wind, except for the swirls, the bright places, the maps of magnetism. They're holding on, billions of years later, still deflecting particles, still resisting the weathering, still showing us what the moon once was, a world with a molten core, a churning dynamo, a protective bubble, a world more like Earth than we imagined. The moon lost its shield, but the memory remains, written in rock, painted in brightness, a library of invisible fields, ghosts that refuse to fade, whispering to us across billions of years, telling us the moon was once alive, in its own way, protected, active, young, and then it wasn't. The moon lost its shield, but it kept its secrets, and for billions of years we could only wonder what lay on the far side. We could only guess, until January of 2019, when China did something no one had ever done before. They landed there. The mission was called Chang'e 4, a lander and a rover named Yutu-2. The target was Von Karman crater, inside the South Pole-Aitken Basin, the oldest, deepest scar on the moon, the most geologically interesting place in the entire lunar system. Not just the far side's most valuable real estate, but there was a problem, and the same problem that had kept the far side untouched for 6 decades. The communication barrier, radio silence. You can't control a lander if you can't talk to it. You can't receive data if the moon is blocking every signal. It's like setting down in a room with no doors or windows, then installing a mirror outside so you could see yourself. The relay satellite made the impossible possible. China solved it months before the landing. They launched a satellite called Queqiao. Beautiful name. It means magpie bridge, a reference to an old story about lovers separated by a river. The magpies form a bridge so they can meet. Queqiao does the same thing, but the bridge is made of radio waves, and the river is the moon itself. Queqiao sits in a halo orbit around Lagrange Point 2. That's a gravitationally stable spot beyond the moon, about 65,000 kilometers farther out. From there, it can see both sides, the far side and Earth, all at once. It's a translator sitting in space, catching signals from the far side and whispering them around the moon to Earth, constantly, without pause. As long as Queqiao is there, the far side isn't silent anymore. On January 3rd, 2019, Chang'e 4 began its descent into Von Karman crater, into shadow and stone. The lander came down slowly, carefully, using autonomous systems. No human could control it in real time. The signal delay through Queqiao was too long. The lander had to think for itself, choose its own landing site, adjust to the terrain, all while falling toward a surface no spacecraft had ever touched. It worked. Chang'e 4 set down softly, right where it was supposed to be, inside the oldest basin on the moon, on ground that had been waiting 4 billion years. The far side wasn't untouched anymore. We'd arrived. Hours later, Yutu-2 rolled down a ramp, a small rover, about 1.5 meters long, weighing 140 kilograms, 6 wheels, a suite of instruments, ground-penetrating radar, cameras, spectrometers, everything needed to study the surface, to dig into the regolith, to read the ancient story written in stone. Yutu-2 is the loneliest rover, trundling across stone no human has ever seen directly, sending postcards through a relay. Every image, every measurement, every grain of data travels up to Queqiao, then around the moon, then down to Earth, a route no other mission had ever needed, a solution to a problem that once seemed impossible. The rover was designed to last 3 months, maybe 6 if they were lucky. It's still going. As of this script, Yutu-2 has been exploring for years, longer than any other lunar rover in history. It moves slowly, a few dozen meters at a time, then it stops, studies the ground, takes measurements, sleeps through the lunar night when temperatures drop to minus 170 Celsius, wakes up when the sun returns, keeps going. What has it found? material from deep inside the moon, rocks that were ejected when the South Pole-Aitken impact punched through the crust, possibly even mantle material, stuff that's normally buried kilometers down, now sitting on the surface, waiting to be analyzed. U-22's spectrometers have identified minerals that don't match the near side, different chemistry, different history. The far side isn't just hidden, it's fundamentally different. The rover has also mapped subsurface layers with its radar, peering down through the regolith, seeing structure, boundaries, evidence of multiple impacts, multiple lava flows, a geological record that goes back billions of years. Each layer is a page in a book we couldn't read before. Now we're reading it, line by line, meter by meter. Chang'e 4 proved something more important than any single discovery. And it proved the far side is accessible. The communication barrier wasn't insurmountable. It just required a relay, a satellite sitting in the right place. Queqiao demonstrated that. Other missions can follow the same path, use the same technique, land anywhere on the far side, explore the entire hemisphere. The door is open now. This wasn't just a technical achievement. It was a shift. For all of human history, the far side was purely theoretical. We knew it existed. We had pictures, but we'd never touched it, never sent anything there that could stay, never explored it the way you explore a place, on the ground, moving through it, feeling the terrain. Chang'e 4 changed that. The far side is no longer purely a frontier of mystery. It's a place we've touched, a place we've driven across, a place where human-made machines are working right now, thinking, moving, measuring, learning, sending their findings back to us through an invisible bridge of radio waves. The magpies are still flying, the signal is still strong, and the loneliest rover in the solar system is still out there, rolling through shadow, exploring stone, writing a new chapter in a story that began when the moon was born. We've made first contact with the far side, and it's speaking to us. The far side isn't just a place we've explored, it's a place we might live. That idea would have sounded absurd even a decade ago. The challenges were too great. Communication was impossible. Landing was a guess. Resources were unknown. But the discoveries of the last few years have changed the calculation. Water ice exists in the shadows, and the radio environment is pristine. Access is proven. The question isn't whether we can build a base on the far side anymore. The question is what that base would look like and what it would mean to live there. Start with the fundamentals. Any lunar base needs three things: power, water, shelter. The far side can provide all three, but in ways that are profoundly different from anywhere humans have lived before. Power comes from the sun. Near the lunar poles, certain peaks receive sunlight almost constantly. These are called the peaks of eternal light. The moon's axis has almost no tilt, just 1.5 degrees. That means the sun never rises high, but it also never sets for long. At the right location, solar panels could generate electricity 24 hours a day. No batteries, no nuclear reactors, just constant, a clean energy from a star that's been burning for 4.5 billion years. Water is harder, but it's there. The ice in permanent shadows is a gift from the cosmos. A tank of rocket fuel buried in stone and waiting for 4 billion years. That ice can be split through electrolysis. Water becomes hydrogen and oxygen. Hydrogen is fuel. Oxygen is breathing air. One resource becomes two, and both are essential for survival. The challenge isn't whether the ice exists. We know it does. The challenge is access. How much can we reach? How deep do we have to dig? Can we extract it without losing most of it to the vacuum? Those are open questions. We don't have answers yet. Shelter is the moon itself. Regolith, the powdery dust that covers the surface, is mostly worthless for growing food, but it's excellent for blocking radiation. A habitat buried under 2 or 3 meters of lunar soil would be shielded from cosmic rays and solar storms. The permanent shadows offer something else too: natural cryogenic storage. Temperatures in those craters never rise above -240 degrees Celsius. That's cold enough to keep biological samples frozen indefinitely, cold enough to preserve fuel without pressurized tanks. The moon provides protection just by being what it is: stone and shadow and ancient cold. The far side offers one more advantage: Silence. The radio-quiet environment isn't just useful for telescopes. It's ideal for deep space communication arrays. A base on the far side could serve as a relay station for missions beyond the Moon. Mars, the asteroid belt, the outer planets. Signals from those places are faint by the time they reach Earth. Our planet is noisy. Radio interference from cities, satellites, and the ionosphere makes detecting weak signals difficult. On the far side, that noise doesn't exist. You could hear a whisper from the edge of the solar system. Picture an installation on the rim of a far-side crater, solar panels along the peaks, habitats dug into the regolith, drills reaching into the shadows, extracting ice, radio dishes pointed at the stars. A human presence where Earth has never been visible. A foothold on the silent hemisphere. That's the promise. The practical case for a far-side base is strong, but there's a challenge that has nothing to do with engineering. The psychological challenge of a far-side base isn't distance, it's absence. Astronauts on the near side, or in orbit, can look up and see Earth, a blue and white marble hanging in the black, a reminder of home, something to anchor you when the isolation becomes unbearable. On the far side, Earth is gone, not over the horizon, behind an entire world. A far-side base would be the first human outpost where Earth is not in the sky. Not distant, not hidden by clouds, but geometrically impossible to see. A place of true alien isolation. The longest any human has experienced this was about 50 minutes. That's 1/2 of a lunar orbit, from the moment Earth disappears behind the Moon until it reappears on the other side. Apollo astronauts went through it. Radio silence. No contact with mission control, no view of home, just the spacecraft and the far side passing below. Michael Collins, orbiting alone while Armstrong and Aldrin walked on the near side, wrote about those moments. Yet he didn't describe them as peaceful. He described them as profoundly lonely. 50 minutes, that's the record. A far side base would mean permanent absence, weeks, months, maybe years. You could walk outside your habitat and look up. The stars would be there. The sun would arc low across the horizon. But Earth would not exist in your sky. You'd know it was there. You'd communicate with it through relays. You'd receive messages, send reports, maybe even see video of the people you left behind. But you'd have to take it on faith. Living on the far side would be like living in a lighthouse that can never see the shore. You'd know Earth exists, but you'd have to take it on faith. We don't know what that does to the mind. Think about that. Humans have lived in isolation before. Antarctica, submarines, space stations. Yeah, but even in those environments, Earth is present. You can see it, feel it through gravity. Look out a window and there it is. On the far side, there's nothing. Just the knowledge that home exists behind an entire planetary body that you'll never see through. This isn't a small question. Mental health determines mission success as much as engineering does. If a crew can't handle the psychological weight of permanent Earth absence, the base fails. We need to study this, simulate it, understand it before we commit people to living there. The open questions are piling up. How much ice is actually accessible? We know it's there, but can we reach it efficiently? Can regolith be processed into effective radiation shielding, or do we need to bring materials from Earth? How do we handle the temperature extremes between sunlit peaks and shadowed craters? What happens if a solar storm hits and the crew needs to take shelter for days? How do we resupply a base that's harder to reach than the near side? And the big one, the one nobody talks about enough. Can humans psychologically endure a place where Earth doesn't exist in their reality? These aren't reasons to give up. They're problems to solve. Every frontier comes with questions. Antarctica was uninhabitable until we learned how to survive there. Low Earth orbit was a death trap until we figured out life support. The far side is no different. It's just asking different questions. The resources are there, the silence is there, the strategic value is there. A far side base isn't science fiction. It's engineering and psychology and logistics. Yet it's solvable, but it's also a threshold. Building a base on the near side would be extraordinary. We'd be living on another world, but we'd still have Earth in the sky. A connection, a visible thread back to where we came from. A far side base cuts that thread. You'd be somewhere no human has ever been, not just physically distant, existentially separate, behind the moon, beyond sight, in a place where the concept of home becomes abstract. That's what makes it important. The far side isn't just another location. It's a test. Can we live somewhere that demands faith instead of sight? Can we build something permanent in a place that offers no comfort of familiarity? Can we thrive in true isolation, knowing that the world we came from is real but invisible? We're closer to answering those questions than we've ever been. And the ice is mapped. The relay satellites are proven. The landing sites are chosen. What's left is the will to go and the courage to stay. Why does the far side matter? Because it's not just a place, it's a question. What happens when a world splits into two? What happens when one side is hidden forever? The moon has been answering for 4 billion years. We only started listening 60 years ago. The moon is a Rosetta Stone for planetary science, a world close enough to touch, old enough to remember the solar system's birth, and strange enough to challenge everything we assume. Every mystery on the far side points to something bigger. Every crater, every basalt plain, every magnetic anomaly is a clue about how planets form, how they evolve, and what makes a world capable of sustaining life. Start with tidal locking. The moon didn't choose to show us one face forever. Physics chose, gravity chose. Over millions of years, Earth's gravitational grip slowed the moon's rotation until it matched its orbit. One revolution, one rotation, locked. That's not rare, that's common. Most exoplanets we discover are tidally locked. Hot Jupiters, massive worlds orbiting so close to their stars that one side is molten and the other frozen. Planets in the habitable zones of red dwarfs, the most common stars in the galaxy, where liquid water could exist. One hemisphere baked under eternal daylight, the other locked in permanent night. Every tidally locked exoplanet we discover echoes the moon's story. One face baked, one frozen, one side known, and one forever hidden. The difference is we can't visit those worlds. We can't send landers, and we can't drill into their surfaces or map their magnetic fields or search their craters for ice. They're light years away, beyond reach, abstract. The moon is here, 3 days away, and it's teaching us what those distant worlds might be like. Consider the asymmetry. The near side has vast dark plains. The far side has almost none. The crust is thicker. The chemistry is different. That shouldn't happen if the moon formed the way we thought it did. A giant impact, debris coalescing, everything cooling evenly. That model predicts symmetry. The moon didn't get the memo. Some models suggest the moon had a second, smaller companion early in its history, a tiny moon orbiting alongside it. Eventually, they collided. Not a violent smash, but a slow merger. The smaller moon splattered across one hemisphere, thickening the crust, creating the asymmetry. It's one explanation. There are others. The point is, the moon's strangeness forces us to rethink simple formation stories. If our closest neighbor is this complicated, what does that mean for worlds we can barely see? The South Pole-Aitken Basin tells a story about violence, not just lunar violence, solar system violence, an impact so massive it nearly cracked the moon in half, 1,500 miles across, 5 miles deep. That's not an isolated event. That's evidence of a chaotic early solar system where impacts like that were common. Planets growing through collision, moons shattered and reformed, water and organics delivered on comets and asteroids smashing into young worlds. The basin isn't just a scar, it's a window into planetary evolution. When you look at the exposed mantle material, you're seeing what's inside other rocky bodies. Mars, Mercury, the terrestrial exoplanets we're finding around other stars. We can't drill into those worlds. The moon lets us see inside without leaving Earth's neighborhood. The cold traps in the polar craters hold another clue. Water ice in shadows that haven't seen sunlight for billions of years. That ice came from somewhere. Comets, asteroids. It was delivered. And if it was delivered to the moon, it was delivered everywhere in the inner solar system. To Earth, to Mars, maybe to Venus before it became an oven. The far side's ice isn't just a resource for future astronauts. It's proof that water delivery was common. that the ingredients for life were scattered across the early solar system like seeds. Think about that. And the same process that filled those craters with ice might have filled Earth's oceans. The magnetic anomalies are puzzling. The moon has no global magnetic field now, but rocks on the far side are magnetized, frozen records of ancient magnetism. That means the moon once had a dynamo, a molten core churning and generating a magnetic field like Earth's does today. Small worlds aren't supposed to do that. They cool too fast. Their cores solidify. The dynamo shuts down. Except the moon did it, which means our assumptions about planetary interiors are incomplete. If a body as small as the moon can generate a magnetic field, what about other moons? What about exoplanets smaller than Earth orbiting distant stars? Magnetic fields matter. They shield surfaces from radiation. They protect atmospheres from being stripped away by stellar winds. Understanding how small worlds generate and lose their magnetic fields helps us understand which exoplanets might be habitable. The far side is a teacher. We just had to learn to listen. Every sample returned from the far side will refine our models of planetary differentiation, how rocky worlds separate into core, mantle, and crust. Every magnetic map will challenge our theories about dynamos. Every ice core will reveal the history of water in the solar system. Every crater will sharpen our understanding of impact rates and planetary bombardment. The moon isn't just a stepping stone to Mars or a testbed for exploration technology. It's a laboratory, a natural experiment in planetary science that's been running for 4.5 billion years. We're finally in a position to read the results. Understanding the moon's far side helps us understand distant exoplanets we'll never visit. Tidal locking isn't rare, it's common. Most planets around red dwarfs, the most common stars, are tidally locked. The moon is our local laboratory for understanding what those worlds might be like. What happens to a surface that never sees sunlight? How materials distribute on a tidally locked body? Whether life could survive in the twilight zone between day and night? The moon has been answering those questions since before life existed on Earth. We're only now asking the right questions back. But questions aren't the end of this story. They're the invitation. Imagine you're standing there, on the far side, the only human for hundreds of thousands of kilometers in any direction. Yet your boots press into regolith that's sat undisturbed for billions of years. Each footprint you make is the first disturbance this ground has known since an asteroid struck, when Earth was still molten. You turn in a slow circle. Mountains rise around you, their peaks catching sunlight that's traveled 93 million miles unobstructed. The sky above is black, perfectly black, the way skies used to be before humans invented cities. Stars everywhere, thousands of them. No atmosphere to make them twinkle. They just burn, steady and cold and ancient. You look for Earth, the blue marble that's been humanity's constant companion since we first looked up. The world that's hung in every sky, visible from every human settlement, present at every moment of human history. It's not there. And that's what tidal locking means in human terms. The moon turned its face toward Earth 4 billion years ago and never looked away. But here, on this far shore, Earth doesn't exist. Not behind you, not above you, not anywhere. The most familiar sight in human experience, the one celestial body we've watched our entire existence, simply absent from your sky. Michael Collins knew a version of this. Orbiting behind the moon, cut off from Houston, from Earth, from every human voice. He was alone for 48 minutes at a time. You could be alone forever here. Stand in one of those permanently shadowed craters, and you'd be surrounded by ice that remembers the solar system's birth, water older than oceans, darkness that sunlight hasn't touched in geological ages. The silence would be complete, not the silence of a quiet room, and not the silence of a forest at night. On Earth, silence is never really silent. There's wind. There's your heartbeat conducted through air into your ears. There's the planet itself, groaning and shifting beneath you. Here, there's nothing. Sound needs air. The far side has none. You could scream and hear nothing but the vibration in your own skull. The universe doesn't carry your voice. It doesn't even notice you're here. Standing on the far side, you'd be the only warm thing for hundreds of kilometers. the only breath, the only heartbeat, the stone around you older than bones, colder than night, silent in ways Earth has never known. And above you, stars. No city lights to drown them, no atmosphere to blur them, no Earth to remind you of home, just you and the cosmos. And the patient stone that has waited 4 billion years for this moment. This is what NASA found on the dark side of the moon. Not aliens, not ancient structures, something more profound. A place that asks us what it means to be human when every familiar thing is stripped away. A shore where we can stand at the edge of everything we know and look outward instead of back. The ice is waiting in those shadows. The craters are waiting to tell their stories. The ancient lava flows are waiting to reveal how worlds are born. We've sent our machines. We've mapped the surface. We've analyzed the chemistry and measured the gravity and photographed the terrain. But someday, a human will stand there, will feel that absence, will look up at a sky without Earth and understand, in a way no data can convey, what it means to be truly elsewhere. The far side has been patient. It's been there since before anything lived, since before Earth had continents or oceans or air worth breathing. It watched our planet transform from hell to haven. It watched life begin. It watched us evolve, build civilizations, develop language and art and science, and finally, the ability to reach across the void, and it's still waiting. If you enjoyed this journey to the far side, consider subscribing. There are more hidden worlds to explore, more silences to break, more stones with stories to tell. Thank you for listening. The invitation stands. Come, descend, discover what has slept untouched since time began.